So the first question is just kind of if you could maybe elaborate a little bit more about the MOXIE experiment in general, and what that
Okay.
looks like.
If I could, I'd like to start with why we need MOXIE, and I think
Sure.
the rest will flow from that. When we go to Mars someday, I mean, my grandchildren, your children, hopefully, it'll be that generation. Um, we need to bring a lot of things with us, of course. This isn't like, this isn't uh, going to an environment that is welcoming or compatible with human beings, and we'll obviously need things like habitat, rovers, a very large power system, and this is important, maybe 25 to 30 kilowatts of power, um, a rocket to take the crew back to space when they're done with their mission. And the way the planets line up, the mission is likely to be a year and a half. So we're talking about long missions. And it turns out that the single largest thing you would need to bring with you is not what people might expect. It's a very large tank of liquid oxygen, tons, 25, 30 tons of liquid oxygen. Now, there's one obvious reason, but that's not the main reason. The obvious reason is that the crew needs to breathe, and there isn't oxygen to be had on Mars to breathe. Um, the less obvious reason is the important one. It's because everything that uses fuel needs a source of what's called an oxidizer, usually oxygen. And on Earth, we don't think about that. When you go off Earth to space, to Mars, to the moon, anywhere, well, now you need to bring your oxygen with you, and it's a lot more than you would think. So, to give you an example, if you were to burn a log that weighs a pound in your fireplace, you would be burning maybe 4 or 5 pounds of oxygen, way more oxygen than the weight of the fuel, the log. The same thing when we eat our lunch, that's a fuel, and we need oxygen, that's why we breathe, to use the fuel to turn it into energy. The big actor here, the big player is the rocket to take the crew back to space. And the way to think about that is think about how much food the crew eats over the course of a year, and then think about how much fuel, this big fuel tank the rocket's going to need, obviously many times more, pounds of fuel than pounds of food, fuel for the rocket. So in the end, it comes down to, for a crew of 4 to 6, that the crew will need a couple of tons of oxygen to breathe. The rocket for its 5 or 6 minutes of firing will use more like 25, 27, 28 tons, something like that. So overall, we need 30 tons of oxygen. And as I said at the beginning, that's the single biggest thing we would need to bring to Mars to have a successful mission and to return our heroes back to us safely. There's another way. And it's long been recognized that there is another way, which is to do what explorers have always done. You bring some things with you, and you use what you find along the way. You live off the land. Okay, the fancy NASA speak for living off the land is the acronym ISRU, In-Situ Resource Utilization. If you think about the words, living off the land. So in this case, well, where do we get oxygen easily? And easily, where is it accessible? That's the important part of the question. Oxygen you can find in any rock you pick up, just about will have oxygen, but getting it out is a problem. So much better to do what the plants do on Earth and the trees do on Earth, which is just to start with carbon dioxide and then somehow convert that in a chemical process to oxygen. That's why we have oxygen to breathe, and that's why we don't on Mars. There aren't seas full of plankton and forests full of trees to make oxygen for us. But not only that, we have very little even carbon dioxide on Mars to begin with. The atmosphere, well, it's a lot of carbon dioxide. It's very little atmosphere. It's about a 0.5% of the amount of atmosphere, of the thickness of the air, as we have on Earth. It's fortunately all carbon dioxide at 96%. So we have lots of carbon dioxide that we can pull out of this thin air. And the trick then is to turn it into oxygen. How do we do that? Well, we can't bring a forest, so we bring MOXIE. And while the rover has very little space for MOXIE, it's the size of maybe a car battery, and it has very little power. I mentioned 25 to 30 kilowatts, I think. That's what we would need for our power plant. The rover has maybe 100 watts, but it's enough to demonstrate that this will actually work. It's kind of an audacious thing. You need to have MOXIE to do this. And so we want to demonstrate that it will work. So what is it? Well, from a technology point of view, it's basically a fuel cell. It's what's called a solid oxide fuel cell. You have a ceramic that gets heated up to 800 degrees. That allows oxygen ions to pass in and out. But we don't run it as a fuel cell. We run it as just the opposite, which you can do with fuel cells. You can run them backwards. And instead of burning fuel or reacting fuel to get electricity, you can put in electricity and react the stable product, carbon dioxide in this case. You can react that to make oxygen and the fuel, which in that case is carbon monoxide. So that's what we do. We turn carbon dioxide through this hot ceramic membrane and all the stuff that surrounds it into oxygen and carbon monoxide. Now, I mean, people that think about the chemistry, the words carbon dioxide tells you there's carbon and 2 oxygens in every molecule. Why not take both oxygens? Well, we don't want to make carbon because it gums up the works and will make the instrument stop working. So the part of the trick is to just carefully detach 1 oxygen atom from each carbon dioxide molecule, not 2. Okay, so that's how it works, and that's why we need to do it.